Okay. So I will be talking about angular dependencies associated with electron. I'll be talking mostly I'll be talking about the theory, but I will also show lots of old results and some new results on that. Okay. So we're talking about an experiment in which there's no orientation of the molecule. So we just have the one scattering data. And one thing to remember about the dissociative attachment angular distribution is that it can be more detailed than a photodissociation cross-section angular dependence. Photodissociation, you just have the one beta parameter, but hypothetically, a number of partial waves may contribute to a dissociative attachment angular dependence. So hypothetically, you can distinguish multiple dynamic effects. You have two dynamic effects that both affect beta, you can't distinguish them. So the more parameters you have in your angular distribution, hypothetically, the more effects you can distinguish. Okay, I'm a dead horse, but I have to write this, talk about it. We have the closed coupling expansion of the wave function that we use in the complex cone method, and importantly, we have these extra terms that go beyond the closed coupling approximation. We have P space, what we call P space, closed coupling approximation, and we call the last term Q space. So when we do the complex cone calculation, we're explicitly solving for the P space part of the wave function. We construct an effective optical potential for P space, which has form like this. So we have we have a projector P that projects upon these target states, and then Q is its complement. So those are what goes into there. So it's an energy dependent countercode. Okay, so to construct this, we have to construct that Green's function. So we do this depending on the size, either explicitly or iteratively. And in general, we use either of two treatments. One, we just include these configurations that are described only by the target orbitals, the orbitals that we use to construct our target states. In addition, we may include all the terms described by single excitations from those configurations to the scattering basis. And we call these last terms the complement of P space because they account for the channels that we haven't explicitly included in the calculation. Okay, now we do the calculation, we get an S matrix, function of energy, and in order to extract the information for any of the dependencies, fit it to a functional form. So here's one such functional form. This is guaranteed to be unitary, this form right here. There's a background S matrix right there times this matrix function right here, where this matrix A is a rank 1 permission matrix. So with time reversal symmetry, S is complex symmetric. So alternatively, we may write something like this, where background S matrix and this B are both complex symmetric. B then has this form. And this is a little bit surprising, I think, at least to me, because with the background S matrix, transform basically conjugate ket or bra in A. So background S matrix is conjugation. Which is interesting. Okay. So in order to do this fit, it's kind of nitty-gritty detail, but first fit the position by choosing one S matrix element. Why I choose one S matrix element as opposed to, say, the eigenphase sum is for the reason that channels may open up, and your eigenphase sum might not be well behaved where the channels open up. So I fit one of the lower energy target state S matrix elements. Okay, so the expression I showed before, without an energy dependence there in the background S matrix, was guaranteed to be unitary. In reality, you may have a resonance that's broad, such that you can't approximate the background S matrix as constant. So to account for that, I just do the ad hoc thing, which is to put an energy dependence on the background S matrix. As a result, the functional form is not constrained to be unitary, but I get a better fit. So that's what I do. And yeah. And so I end up fitting this permission matrix A. So constraining that to be permission, the resulting fit is also not guaranteed to be complex symmetric. But again, I'm just trying to get this fit. But that's my perspective. Okay, so we have this matrix A, rank 1 permission. These complex numbers here are partial amplitudes. First order, they correspond to a matrix element between a background scattering wave function and a discrete resonant state. Now, you get these partial amplitudes in the spherical harmonic basis, and you put the usual transformation obtaining those partial amplitudes as a function of direction in the molecular frame. And so, with that, the attachment probability in the molecular frame is just the absolute value of that squared. Or any constants results. Okay, so now I'll talk about what this can tell us about the angular distributions. Now, we've all heard a lot about axial recoil in general, but specifically how this is treated here is that we basically average over orientations of the molecule here. That's basically the third Euler angle. And so basically you integrate that thing, which I should have said is in fact the attachment probability, d phi. So we get a result that is a function of one variable k. And so this is the recoil vector I've chosen to be axial here. Generally, you could pick a non-axial direction and do the same thing. So this works well for certain molecules and doesn't for others. For instance, the double V1 state of water works very well. And also, here I have an example of calculation on angular distributions of dissociative combination, CF plus. And here we have, at least qualitative agreement, we have a prominent forward peak and a less prominent backward peak, which stays right now. Okay, now I'll talk about the simplest case of axial recoil violation that I've worked with. Here's the attachment probability for the double A1 state of water anion. What you can see here is that this lobe is actually bigger. It's got some width of the page. So there's actually a much greater probability for attachment from the top here. And so talking about the oxygen, it's most likely, if the oxygen behaves as per axial recoil, then you'd expect the electron to attach to the top here, and the oxygen to recoil in the backwards direction. However, that's not what the experiment observes. The experiment observes, this is the experiment of Hidehito, Adamya, and Harvard-Smithsonian Center at LBNL. The experiment shows that O- is produced actually in the forward direction. This leads to the conclusion that the breakup is actually anti-axial recoil. In other words, it goes like this. And so that shows that by comparing experiment to theory, we can make a conclusion about the polyatomic dissociation dynamics. Okay, so we've also done some fun mechanical calculations on dissociative attachment. Now, if this entrance amplitude, partial amplitude there, does factor according to an angular function and a function of coordinates, then likewise, and if we assume axial recoil, we have an expression for the cross-section which is schematically this. We have an angular part times the result of what we do is a wave function propagation to construct the Green's function and get cross-section from that. So it's just an angular factor times the cross-sections. Here I show cross-sections for various vibration states. So each of those would have the same angular dependence. Okay, so now to go beyond the simplest axial recoil approximation, we want to take account of two possible effects. One in which the entrance amplitude does not in fact factor well as a product of an angular function and a function of the coordinates. I'll show that taking account of this in -1 or semi-classical means. And also, we can have a recoil angle that does in fact vary with geometry. Whereas the recoil angle is not constant, if you like, over the Franklin region. Okay, so here's an example of that. So if we can't factor the angular part out of the integral, the propagational area, you have to keep it in right here. So if I fix theta, and then if I fix theta, I didn't have a prediction for that theta. So here I've done a calculation on hydrogen sulfide at two angles here, and we have a different initial state, so we have a different final state, and you can see that the cross sections are indeed angle dependent. Okay. Now, I've already mentioned the AA1 and the B1 states of water. Here we have the three potential energy surfaces of these states in C2B geometry. See, this B1 state does have a shallow minimum there. The equilibrium geometry is neutral, so that's consistent with the axial recoil that we found. See also that AA1 does in fact slope down to linear, so that's consistent with the backward scissoring function that we saw. Now on the B2, you have the opportunity to either transit through the intersection or not. So you have either two final states, the B2 or the AA1. So to predict angular distributions for this process, I've done trajectory calculations using classical trajectory calculations using Tully's view of switches on these two coupled potential energy surfaces. So, according to the Wigner distribution, I choose a set of initial conditions. What I have here is actually not. I have here the trajectories in the space-fixed frame. So I start with the water molecule right there, and I'm plotting the directions in which the hydrogens and the oxygen stays there. It's heavy. The directions in which the hydrogens go. So you can see here that there is a fairly obvious qualitative difference between these two. You see that the trajectories here on the left, these are the ones that have transited to the doublet, the A1, the lower state. You see that they do come out at a tighter angle, whereas these guys are coming out at a broader angle. So if we calculate the recoil direction as a function of, we calculate the recoil direction for every trajectory, we can bend those trajectories according to final state, therefore producing different recoil frame attachment probabilities. In other words, as for each trajectory, we have a recoil direction, and we rotate the entrance amplitude such that we define phi as the azimuthal coordinate around that direction. So with that, we do a bunch of trajectories and average them. So on the left, I show here what the axial recoil result would be for the B2 state. That is, of course, independent of final state. But when we do this averaging over classical trajectories, fitting them by final state, we get differences between the two. I have here the B2 state is the green. We have the CS symmetry labels. And the A1 is the blue. Okay, so when we compare this to, Okay, so when we compare this to experiment, we do indeed get qualitative agreement, drawing your attention to this middle peak right here. So for if the dynamic stays on the B2 surface, we see that peak. This is the B2 data. We see that peak at relatively an angle short of 90 degrees. Whereas those on the AA1 state, arguably you could say that peak has shifted further in the backwards direction, in both theory and experiment. So this does demonstrate the routing of trajectories through that conical intersection. We should just go back to that figure. So as you can see on the level B, the two states going to go through the conical intersection. It does indeed have to bend. So this is going to reorient the trajectory further in the backward direction. Okay, this is going to be short. Here I have recent results on methanol. So methanol has a lowest energy resonance of A double prime symmetry. So I'm using the CS point group. So when I do the axial recoil calculation for that at the equilibrium geometry, I necessarily get zeros at 0 and 1/8 in the forward and backwards direction. That's a consequence of there being a node in the plane of the molecule. However, as you can see here, the experiment is non-zero in forward and backwards directions. So this indicates that in order to reproduce the experiment, we have to include the asymmetric vibrational modes, those that break CS symmetry. So basically, to do that, we just average over nuclear geometries. So it's impossible to do nuclear body. And specifically what I do, we have the lowest energy mode here, which is a CH3 rotation. So what I do, operationally speaking, is to fix that rotation angle, and then I average over 6 additional modes of the system. When I do that, I just use true point Hermite quadrature. So in other words, I'm doing a product grid, 2 points in each normal node. So that gives 64 runs, complex cone runs per twist. 5 values a twist, it's 320 geometries. 20 energies per point, that's 6,400 individual populations. Then, given the temperature of the experiment, I average over CH3 rotation angles. So hypothetically, this could produce a prediction for the temperature dependence. It could agree a little better. Okay, the methanol results are indeed not converged. So first of all, they're not converged with respect to the average over vibrational modes. However, in other words, when I add some symmetric modes in there, I don't exactly get the same thing. So, but unfortunately, if I were to do the same thing, 2-point Hermite product grid, this would entail 4,096 calculations, complex cone runs per twist. I'm doing 20 energies per point, that's 80,000. So I can't do that on one processor. I have to use a supercomputer. Also now, this is the reason I referred to it before, the calculation right now with the complement of P-space is substantially different from that without. Now that's not too surprising. In scattering calculations shown here, this was only one channel calculation, so this is my initial go. So we don't even have the apparent state of the resonance here. Whereas with complement P-space, it is effectively included in the optical potential. So that's unfortunate. It is indeed converged with respect to partial waves, only at the G wave. That's kind of surprising that I only had to do that. So in the future, because I can do P-space, I don't use a supercomputer. I just want to probably add a couple more target states such that I hopefully get closer to this result of the complement. Okay, so when I do that, so here's a plot of what I get compared with the experiment when I fix the CH3 rotation angle and average over the other asymmetric modes. You see here qualitative, perhaps, agreement, of course, on 0 forward and backward directions, and you got a peak. So, terrible. Let's get that. Okay, so then we do the, I do that average, given the temperature over the CH3 rotation, and that produces the final prediction. Now I can vary the recoil angle, so this plot, what I show is that for axial recoil. When I vary the recoil angle, I do see some substantial changes there, and arguably this red line is closer to the experiment. So we'd like to draw the conclusion then that the recoil is indeed 15 degrees from axial. And to corroborate this, you just need to take a gradient of the potential energy surface. That's it. Actually, okay, I'll show one more thing. Well, no, we'll be on time now. Okay, so I just want to thank my group. We have new postdocs, Zhuang Li and Qi Wan. Zhuang Li is unrecognizable because he lost his life. And I want to thank everybody else too. And thanks to Solomon for funding, for organizing, DOE for funding, and you for your time.
Question?
Dan, you mentioned that you use the Wigner distribution to sample the trajectories. What do you do with the negative probability parts of that?
This is just the ground state wave function. So there are no negative probability.
Is that right?
Yeah.
For the ground state of an oscillator.
No. Negative.
Yeah. I wanted to ask you, you say you are fitting S matrix instead of eigenphases because eigenphases have this threshold.
They have physical threshold behavior. Or
Threshold,
numerical
but
behavior.
S matrix also has threshold behavior. So
It does, but there's also, it's more numerical.
Uh-huh.
You know, I mean, it's just harder to, I mean, on one hand, I could put that threshold behavior in there, or on the other hand, I could just not.
Yeah, so for S matrix you can put it in, so it's easier to fit S matrix rather than eigenphases.
Well, yeah, but that's the thing. When a channel does open up,
Yeah.
you get a
Right.
you get a cusp in the
Right.
eigenphase sum. So I could account for that, but that would entail an additional parameter.
Mhm.
So it's just easier.
Any other questions? If not, let's thank our speaker again.